2 plus 4 plus 8, and continue on, adding the next power of 2 up to infinity. This might seem crazy, but there's a sense in which this infinite sum equals -1. If you're like me, this feels strange or obviously false when you first see it. But I promise you, by the end of this video, you and I will make it make sense. To do this, we need to back up, and you and I will walk through what it might feel like to discover convergent infinite sums, those ones that at least seem to make sense, to define what they really mean, then to discover this crazy equation and stumble upon new forms of math where it makes sense. Imagine that you are an early mathematician in the process of discovering that 1/2 plus 1/4 plus 1/8 plus 1/16 on and on up to infinity, whatever that means, equals 1. And imagine that you needed to define what it means to add infinitely many things for your friends to take you seriously. What would that feel like? Frankly, I have no idea, and I imagine that more than anything, it feels like being wrong or stuck most of the time. But I'll give my best guess at one way that the successful parts of it might go. One day, you are pondering the nature of distances between objects, and how no matter how close two things are, it seems that they can always be brought a little bit closer together without touching. Fond of math as you are, you want to capture this paradoxical feeling with numbers. So you imagine placing the two objects on the number line, the first at 0, the second at 1. Then, you march the first object towards the second, such that with each step, the distance between them is cut in half. You keep track of the numbers this object touches during its march, writing down 1/2, 1/2 plus a fourth, 1/2 plus a fourth plus an eighth, and so on. That is, each number is naturally written as a slightly longer sum with one more power of 2 in it. As such, you're tempted to say that if these numbers approach anything, we should be able to write this thing down as a sum that contains the reciprocal of every power of 2. On the other hand, we can see geometrically that these numbers approach 1, so what you want to say is that 1 and some kind of infinite sum are the same thing. If your education was too formal, you'd write the statement off as ridiculous. Clearly, you can't add infinitely many things. No human, computer, or physical thing ever could perform such a task. If, however, you approach math with a healthy irreverence, you'll stand brave in the face of ridiculousness and try to make sense out of this nonsense that you wrote down, since it kind of feels like nature gave it to you. So how exactly do you, dear mathematician, go about defining infinite sums? Well practiced in math that you are, you know that finding the right definitions is less about generating new thoughts than it is about dissecting old thoughts, so you go back to how you came across this fuzzy discovery. At no point did you actually perform infinitely many operations. You had a list of numbers, a list that could keep going forever if you had the time, and each number came from a perfectly reasonable finite sum. You noticed that the numbers in this list approach 1, but what do you mean by approach? It's not just that the distance between each number and 1 gets smaller, because, for that matter, the distance between each number and 2 also gets smaller. After thinking about it, you realize what makes 1 special is that your numbers can get arbitrarily close to 1, which is to say, no matter how small your desired distance, 1/100th, 1/1,000,000th, or 1 over the largest number you could write down, if you go down your list long enough, the numbers will eventually fall within that tiny distance of 1. Retrospectively, this might seem like the clear way to solidify what you mean by approach, but as a first-time endeavor, it's actually incredibly clever. Now you pull out your pen and scribble down the definition for what it means for an infinite sum to equal some number, say x. It means that when you generate a list of numbers by cutting off your sum at finite points, the numbers in this list approach x in the sense that no matter how small the distance you choose, at some point down the list, all the numbers start falling within that distance of x. In doing this, you just invented some math. But it never felt like you were pulling things out of thin air. You were just trying to justify what it was that the universe gave you in the first place. You might wonder if you can find other, more general truths about these infinite sums that you just invented. To do so, you look for where you made any arbitrary decisions. For instance, when you were shrinking the distance between your objects, cutting the interval into pieces of size 1/2, 1/4, etc., you could have chosen a proportion other than 1/2. you could have instead cut your interval into pieces of size 9/10 and 1/10, and then cut that rightmost piece into the same proportions, giving you smaller pieces of size 9/100 and 1/100. Then cut that tiny piece of size 1/100 similarly. Continuing on and on, you'd see that 9/10 plus 9/100 plus 9/1000, on and on up to infinity, equals 1, a fact more popularly written as 0.9 repeating equals 1. To all of your friends who insist that this doesn't equal 1 and it just approaches it, you can now just smile, because you know that with infinite sums, to approach and to equal mean the same thing. To be general about it, let's say that you cut your interval into pieces of size p and 1 minus p, where p represents any number between 0 and 1. Cutting the piece of size p in similar proportions, we now get pieces of size p times 1 minus p and p squared. Continuing in this fashion, always cutting up the rightmost piece into those same proportions, you'll find that 1 minus p plus p times 1 minus p plus p squared times 1 minus p, on and on, always adding p to the next power times 1 minus p, equals 1. Dividing both sides by 1 minus p, we get this nice formula. In this formula, the universe is offered a weird form of nonsense. Even though the way that you discovered it only makes sense for values of p between 0 and 1, the right-hand side still makes sense when you replace p with any other number, except maybe for 1. For instance, plugging in -1, the equation reads 1 minus 1 plus 1 minus 1, on and on forever, alternating between the two, equals 1/2. Which feels both pretty silly and kind of like the only thing that it could be. Plugging in 2, the equation reads 1 plus 2 plus 4 plus 8, on and on to infinity, equals -1, something which doesn't even seem reasonable. On the one hand, rigor would dictate that you ignore these, since the definition of infinite sums doesn't apply in these cases. The list of numbers that you generate by cutting off the sum at finite points doesn't approach anything. But you're a mathematician, not a robot, so you don't let the fact that something is nonsensical stop you. I will leave this sum for another day, so that we can jump directly into this monster. First, to clean things up, notice what you get when you cut off the sum at finite points. 1, 3, 7, 15, 31. They're all 1 less than a power of 2. In general, when you add up the first n powers of 2, you get 2 to the n plus 1 minus 1, which this animation hopefully makes clear. You decide to humor the universe and pretend that these numbers, all 1 less than a power of 2, actually do approach -1. It will prove to be cleaner if we add 1 to everything and say that the powers of 2 approach 0. Is there any way that this can make sense? In effect, what you're trying to do is make this formula more general, by saying that it applies to all numbers, not just those between 0 and 1. Again, to make things more general, you look for any place where you made an arbitrary choice. Here, that place turns out to be very sneaky. So sneaky, in fact, that it took mathematicians until the 20th century to find it. It's the way that we define distance between two rational numbers. That is to say, organizing them on a line might not be the only reasonable way to organize them. The notion of distance is essentially a function that takes in two numbers and outputs a number indicating how far apart they are. You could come up with a completely random notion of distance, where 2 is 7 away from 3 and 1/2 is 4/5 away from 100 and all sorts of things. But if you want to actually use a new distance function the way that you use the familiar distance function, it should share some of the same properties. For example, the distance between two numbers shouldn't change if you shift them both by the same amount. So 0 and 4 should be the same distance away as 1 and 5, or 2 and 6, even if that same distance is something other than 4 as we're used to. Keeping things general, the distance between two numbers shouldn't change if you add the same amount to both of them. Let's call this property shift invariance. There are other properties that you want your notion of distance to have as well, like the triangle inequality, but before we start worrying about those, let's start imagining what notion of distance could possibly make powers of 2 approach 0, and which is shift invariant. At first, you might toil for a while to find a frame of mind where this doesn't feel like utter nonsense, but with enough time and a bit of luck, you might think to organize your numbers into rooms, subrooms, sub-subrooms, and so on. You think of 0 as being in the same room as all of the powers of 2 greater than 1, as being in the same subroom as all powers of 2 greater than 2, as being in the same sub-subroom as powers of 2 greater than 4, and so on, with infinitely many smaller and smaller rooms. It's pretty hard to draw infinitely many things, so I'm only going to draw 4 room sizes, but keep in the back of your mind that this process should be able to go on forever. If we think of every number as lying in a hierarchy of rooms, not just 0, shift invariance will tell us where all of the numbers must fall. For instance, 1 should be as far away from 3 as 2 is from 0. Likewise, the distance between 0 and 4 should be the same as that between 1 and 5, 2 and 6, and 3 and 7. Continuing like this, you'll see which rooms, subrooms, sub-subrooms, and so on, successive numbers must fall into. You can also deduce where negative numbers must fall. For example, -1 has to be in the same room as 1, in the same subroom as 3, the same sub-subroom as 7, and so on, always in smaller and smaller rooms with numbers 1 less than a power of 2, because 0 is in smaller and smaller rooms with the powers of 2. So, how do you turn this general idea of closeness based on rooms and subrooms into an actual distance function? You can't take this drawing too literally, since it makes 1 look very close to 14 and 0 very far from 13, even though shift invariance should imply that they're the same distance away. Again, in the actual process of discovery, you might toil away, scribbling through many sheets of paper. But if you have the idea that the only thing which should matter in determining the distance between two objects is the size of the smallest room they share, you might come up with the following. Any numbers lying in different large yellow rooms are a distance 1 from each other. Those which are in the same large room, but not in the same orange subroom, are a distance 1/2 from each other. Those that are in the same orange subroom, but not in the same sub-subroom, are a distance 1/4 from each other. And you continue like this, using the reciprocals of larger and larger powers of 2 to indicate closeness. We won't do it in this video, but see if you can reason about which rooms other rational numbers, like 1/3 and 1/2, should fall into. And see if you can prove why this notion of distance satisfies many of the nice properties we expect from a distance function, like the triangle inequality. Here, I'll just say that this notion of distance is a perfectly legitimate one. We call it the two-adic metric, and it falls into a general family of distance functions called the p-adic metrics, where p stands for any prime number. These metrics give rise to a completely new type of number, neither real nor complex, and have become a central notion in modern number theory. Using the two-adic metric, the fact that the sum of all powers of 2 equals -1 actually makes sense, because the numbers 1, 3, 7, 15, 31, and so on genuinely approach -1. This parable does not actually portray the historical trajectory of discoveries, but nevertheless, I still think it's a good illustration of a recurring pattern in the discovery of math. First, nature hands you something that's ill-defined or even nonsensical. Then you define new concepts that make this fuzzy discovery make sense, and these new concepts tend to yield genuinely useful math and broaden your mind about traditional notions. So, in answer to the age-old question of whether math is invention or discovery, my personal belief is that discovery of non-rigorous truths is what leads us to the construction of rigorous terms that are useful, opening the door for more fuzzy discoveries, continuing the cycle. Every year, more than 100 countries send 6 of their brightest teenagers, or the occasional prepubescent prodigy, to represent them at the International Math Olympiad, commonly known as the IMO. Considering that each country has its own elaborate system of contests leading to their choice of 6 representatives, the IMO stands as the culminating symbol for the surprisingly expansive and wonderful world that is contest math. The contest itself is essentially a test, split over 2 days, with 3 questions given over 4.5 hours each day. The questions are all proofs, meaning you don't simply find some numerical answer. You have to discover and articulate a rigorous line of reasoning to answer each difficult question, and then each one is scored on a scale from 0 up to 7. Of interest to you and me today is the one from 2011, with 563 total participants representing 101 countries. I know what you're thinking, and the answer is yes. Those do all happen to be prime numbers. But that's not why this test was interesting. Out of all these prime problem solvers, only one of them, Lisa Sauermann from Germany, got a perfect score. And the only thing standing between the next 2 runners-up that year and a perfect score was problem number 2. And this problem is beautiful. And despite evading many of the world's best mathematicians of their age, the solution is something that anyone watching this video can understand. So let's begin by reading through it carefully. Let S be a finite set of at least 2 points on the plane. Okay, so as you read the question, it's often helpful to start drawing an example for yourself. Assume that no 3 points of S are collinear. In other words, you never have 3 points lining up. So you can probably predict that the problem's going to involve drawing lines in some way that 3 points on one line would mess things up. A windmill is a process that starts with the line L going through a single point P in S. The line rotates clockwise around the pivot P until the first time that that line meets some other point belonging to S. And again, while reading, it's helpful to draw out an example. So we've got this line that's pivoting around some point until it hits another. This point, Q, takes over as the new pivot, and the line now rotates clockwise about Q until it next meets a point of S. This process continues indefinitely. Alright, that's kind of fun. We keep rotating and changing the pivot, and you can see why they call it a windmill process, and you can also see why they specified that no 3 points lie on one line. You wouldn't want to run into the ambiguity where you don't know which pivot to switch to. Okay, so with all this setup, what's the question? Show that we can choose a point P in S and a line L going through P such that the resulting windmill uses each point of S as a pivot infinitely many times. Alright. Depending on your tolerance of puzzles for puzzle's sake, you might wonder, why would anyone care about such a question? There's a very good reason, in fact. I would argue that the act of solving this will make you better at math and related fields, and I'll explain why once you've seen the solution. But certainly on the surface, it feels disconnected from other parts of math. I mean, you look at other Olympiad problems and they often involve some function to analyze or a numerical pattern to deduce, maybe a difficult counting setup or an elaborate geometric construction. But problem 2, it's an unusually pure puzzle. And in some ways, that's its charm. Proving that some initial condition will result in this windmill hitting all the points infinitely many times, well, that doesn't test your knowledge of a particular theorem. It tests if you can find a clever perspective. But that blade cuts both ways. Without resting on an existing result from math, what could possibly prepare someone to study for something like this? And in fact, that brings us to the second unusual thing about this problem. Based on the results, I'm guessing that it turned out to be much harder than the contest organizers expected. You see, typically, the 3 problems each day are supposed to get progressively harder. They're all hard, of course, it's the IMO, but problems 1 and 4, they should be doable. Problems 2 and 5, they're challenging. And problems 3 and 6, well, they can be brutal. But take a look at how many of our 563 participants that year got perfect scores on each of the problems. Only 22 of them got full marks for question number 2. By contrast, 170 got a perfect score on problem 5, which is supposed to be about the same difficulty, and more than twice as many got a perfect score for problem 3, which is supposed to be harder. Some of you might notice that only 6 students got full points for problem 6 that year, so by some measure that was the hardest problem on the test. In fact, the way I introduced things earlier was a little disingenuous. The full data would suggest that problem 6 was the real clincher. But what's strange is that if you look at the results of those 6 students who solved this hardest problem, all of whom are clearly phenomenal, world-class problem solvers. This windmill puzzle evaded 5 out of 6 of them. But again, this problem is not hard because of the background knowledge it demands. It asks only for insight. So how do you approach something like this? The first step with any puzzle is to simply play around with it and get a feel for it. And it's always good to start simple and slowly get more complicated from there. The simplest case would be 2 points, where the line trades off between each point. And that works well enough. Adding a third point, it's pretty clear that the line will just rotate around them. It might not be entirely clear how you would phrase this as a rigorous proof yet, but right now we're just getting a feel for things. The fourth point is where it gets interesting. In some places, your windmill will go around the 4 points just like it did with the triangle. But if we put it inside that triangle, it looks like our windmill never hits it. Looking back at the problem, it's asking you to show that for some starting position of the line, not any position, the process will hit all the points infinitely many times. So for an example like this, if you start with the line going through that troublesome middle point, what happens? And again, at this point, we're just playing around, perhaps moving your pencil among dots that you've drawn on a piece of scratch paper. You want to believe a result before you try too hard to prove it. Here, you'd see that your windmill does indeed bounce off of all of the points as it goes through a cycle, and it ends up back where it started. The worry you might have is that in some large sets of points, where some are kind of inside the others, you might be able to start off on the inside, but maybe something about this windmill process takes the line to the outside, where as time goes on to infinity, it'll be blocked off from those inner points. If you play around, and mind you, it can take some time to draw out many examples and think this through, you would notice that when the line starts off passing through the middle of the points, it tends to stay there. It never seems to venture off to the outside. But can you guarantee that this will always happen? Or rather, can you first make this idea of starting in the middle a little bit more rigorous, and from there prove that all the points will be hit infinitely many times? As a general problem-solving tip, whenever you have a vague idea that feels productive, you should of course find a way to be more exact about what you're saying, but preferably put numbers to it, and then see if you can ask questions about those numbers. In our example, one way to formalize this idea of a middle is to count how many points are on either side of the line. If you give the line some orientation, you can reasonably talk about a left half, say coloring all the points of the left blue, and a right half, say coloring all the points on the right brown. And what it means for a line to be in the middle is that there are as many blue points as there are brown points. For the moment, let's say that the total number of points is an odd number, and the point that the line passes through is colored white, sort of a neutral color. So for example, if there were 11 points, you would have 5 blue ones on the left, 5 brown ones on the right, and the single white point as the pivot. The case with an even number of points will be similar, just slightly less symmetric. What this gives us is a new question to ask. What happens to the number of blue points and brown points as the process plays out? In the example on screen now, you might notice it's always 5 and 5, never changing. Playing around with other examples, you would find that the same is true. Take a moment to pause right now and see if you can think through why exactly that would happen. Why would these numbers not change? Well, the key is to think through what happens as the line changes its pivot. Having given the line an orientation, we can talk reasonably about which half is above the pivot and which one is below. If the line hits a blue point on its left, it must happen below the pivot. So then when it changes the pivot and continues rotating clockwise a bit, that old pivot, now above the new one, ends up to the left, meaning it ends up in the blue region. And entirely symmetrically, when it hits a brown point, it happens above the pivot, meaning that the old pivot ends up in the brown region. So no matter what, the number of points on a given side of the line, that cannot change. except for the instances where the line's passing through 2 points at once. When you lose a blue point, you gain a new one. When you lose a brown point, you gain a new one. And that is our key insight number 1. So why would this imply that the line must hit every point infinitely many times, no matter what weird set of points you could dream up? Well, the second key is to think about letting this process go until the line has turned 180 degrees around. What that means is it's parallel to the starting position, and because it has to remain the case that half the points are on one side and half the points are on the other, it must be passing through the same point it started on. I mean, think about it. If it ended up on some other point, it would change the number on a given side. Additionally, since the line has rotated halfway around, everything that was blue has become brown, and everything which was brown has become blue. And the only way to change a color is if you get hit by the line. So, for our odd-numbered case, that means that after a half rotation, the line is back where it started, and it's hit all of the other points. So as time moves forward, it repeats this exact set of motions over and over, hitting all of those points infinitely many times. For the case with an even number of points, we need to alter the scheme slightly, but only slightly. To make it so that the number of blues can equal the number of browns, let's say that the pivot counts now as a brown point. So to define our initial condition, we still say for a given angle of the line, select an initial point so that half of the points are blue, all on the left, and half of them are brown, now either meaning they're on the right or the pivot. The same argument from before implies that after a 180 degree turn, everything has swapped colors. But this time, the line will be passing through a different point after that first half turn, specifically one that used to be blue. But after another 180 degrees, it has to be passing through the one that it started on. Again, the logic is that it's parallel to its starting position, and if it was passing through any other point, the number of points on a given side would have to be different. So once more, we have a cycle which hits all of the points and which ends in the same position where it started. This time it takes 360 degrees, but that doesn't matter. As the cycle continues, it'll hit all the points infinitely many times. Stepping back, there are 2 important lessons to take away from this puzzle. The first one social and the second one mathematical. Once you know this solution, and if you kind of ponder it a bit and turn it around in your head a couple times, it's very easy to fool yourself into thinking that the problem is easier than it is. After all, of course the number of points on a given side stays constant, right? Of course that's a question you would ask. And of course when you start in the middle, every point will switch sides after a half a turn. But the advantage of this problem coming from the IMO is that we don't have to rest on subjective statements. We have the data to show it's a genuinely hard problem, in that it evaded many of the world's best students who are demonstrably able to solve hard problems. In math, it is extremely hard to empathize with what it feels like to not understand something. I was discussing this video with a former coworker of mine from Khan Academy who worked a lot with people creating math exercises. And he pointed out that across a wide variety of contributors, there's one constant. Nobody is able to tell how difficult their exercises are. Knowing when math is hard is way harder than the math itself. This is important to keep in mind when teaching, but it's equally important to keep in mind when being taught. On our windmill puzzle, even if counting the number of points on one side seems obvious in hindsight, you have to ask, given the vast space of possible things you might consider, why would anyone's mind turn to that particular idea? This brings us to the mathematical takeaway. What ultimately led to the solution was finding something about the complex system which stays constant during this chaotic unfolding. This is a ubiquitous theme through math and especially through physics. We're finding what's called an invariant. Topologists do this when they count the number of holes in a surface. Physicists do this when they define the ideas of energy and momentum, or in special relativity, when they define more abstract ideas like proper time. As a student, it's easy to take for granted the definitions handed down to you. But the more puzzles you solve where the insight involves an invariant, the more you come to appreciate that each one of these definitions was once a clever discovery. Terence Tao, one of the greatest modern mathematicians and the world's youngest IMO medalist, wrote that mathematical problems, or puzzles, are important to real mathematics, like solving real-life problems, just as fables, stories, and anecdotes are important to the young in understanding real life. Sure, these kinds of puzzles are contrived, but they carry lessons relevant to useful problems you may actually need to solve one day. Maybe it seems silly to liken this windmill puzzle to a fairy tale,